Okay, we'll begin. Are there questions? Okay. Yeah, go ahead.
Sir, last time what we were discussing that maybe we could have had like 2 points at the different last scattering surface, opposite sides,
Yes.
instead of bringing them back to the same like starting point before inflation. Suppose they were actually in different like different horizons, like
Okay.
they didn't have a common horizon.
Yes.
So even then, if we let's say we start at phi 1 and phi 2 at the 2 points, the inflation field,
Yeah.
and it goes up, the time difference that it takes to get to the reheating is very small.
Yes.
So that will not be visible today. Like, I mean, I think so.
No, it will be visible. See, the point is if the difference was of order 1, yeah, if the difference was small, of course, then it will not be small. But we are assuming that, I mean, if there is no correlation, then the difference need not be small, right? I mean, then what sets the difference to be small?
I mean, no matter the like, at some let's say lambda star, what at start of inflation something,
Yeah.
there is some order one or whatever order difference.
Yes.
That difference will also get suppressed. I mean, the effect of it will get suppressed during inflation. After inflation.
Yeah, but only if the particles are causally connected. So otherwise, the difference cannot get suppressed, right? Because any signal propagates at the speed of light.
No, it is not getting suppressed because there is some interaction going on, but rather because the field phi, I mean, the potential is same everywhere, like in space time.
Yes, but if you start at different phi to begin with,
Yeah.
right, then in order to uniformize, right, see the point 1 has to know that the phi at point 2 is different, right?
I mean, even I'm saying that even without knowing, no matter how different it may be,
Hmm.
that difference will get suppressed regardless of whether they are causally connected or not.
How?
Because inflation does that, right? Because when it blows up, the like from lambda star to lambda I,
Hmm.
even that information will get lost. It's not about causally connecting the two
See,
points.
the inflation blows up small regions, right? But if you look at in the co-moving coordinate, if 2 points are at certain co-moving separation, unless they are causally connected, see, okay, let's suppose that at one point the value of phi is phi 1 and the other point is phi 2, right? So you
Yeah.
are saying that phi 1 will change back to phi 2 or phi 2 will change back to phi 1.
No, actually, both of them will go to some common phi, but in different times. Like, which is the lambda I point. Eventually, all regardless of the beginning
Yeah,
value of phi.
okay. Yeah, true. That's true. But there will be difference in the time.
Yeah, and that difference will be so small that, I mean, let's say one of the phi's reaches that lambda I point first, and the other reaches after that. They don't know about that, but today we can observe that in principle. But that difference is very small.
Why? Because look at this region, right? I mean, suppose you look at the V versus phi, V versus phi, right? And you have something like this, potential like this. Okay? Imagine that you start from here. Okay, suppose this is phi 1. It reaches at certain time, right? It
Yeah,
reaches at this region at certain time.
yeah, that is some
Now,
phi I.
yeah, that's the end, right? That is fixed. Now, suppose there is another point in space where it starts here, right? Phi 2.
Yeah.
Then the time difference that we are talking about is the time difference that it takes for the field phi to roll from phi 2 to phi 1,
Yeah, effectively.
right? But that difference can be large in general. It's a slow, I mean, it's a slow roll, right?
I mean, we know that lambda star of for both phi 1 and phi 2, like lambda 1 star and lambda 2 star, are very small. I mean, we know the time of inflation, like lambda is some exponential v naught t sort of
Lambda
a.
star is small, right? So let's look at a fixed lambda. Okay, you are saying at fixed lambda, right? Say at lambda star, phi 1 was here, phi 2 was there. right?
Yeah.
Phi at one point was here, phi at another point was there. After that, in terms of time, you can see clearly, right, that the time that it takes for the phi to roll from phi 2 to phi 1 is what you are talking about, right? That will be the order of difference in the time at which the inflation ends.
Yeah, and that will be something exponentially minus v naught. No, wait, I'll have to think the exact number, but
No, because see, V naught doesn't affect at all, right? Because the gradient is what matters here, right? The gradient of the potential, V prime, and we are assuming that V prime is small. So in general, if you start with phi 1 and phi 2 at generic points, right, there will be a large time difference between the time that inflation ends, and that will translate to inhomogeneities in the microwave background.
sir, I mean, from phi 2 to phi I, the total time is already very small. I mean, the bound at least.
No, you don't know that.
No, the bound we know, right? That it should be greater than some number,
Yes,
and that number is quite small. I mean, as far as I know.
it need not be, right?
I mean, the bound has fixed, right? I mean,
The lower bound is fixed.
yeah. I'm talking about the lower bound.
Yes.
That is very small.
Yeah, but even if that is very small, right? I mean, at this time, right, all of these are very small, right? It's a question of the ratio of lambda. So lambda I of the point 1 over lambda I at the point 2. Okay? That's what you're talking about. And this
Sort of,
ratio
yeah.
can be large. Right?
I mean, I was saying that it might not be large given that lambda star to begin, like if lambda
Okay.
star at 1 and lambda star at 2 were arbitrarily like in proportion, like maybe 2 lambda star or something like that,
Yeah, yeah.
then lambda I won't show that 2 factor
Why not?
because it is evolving exponentially in time.
Yeah, okay. Let me put it this way. Okay. So you are saying that because it's microscopic physics, the difference is small. Okay. But at this time, okay, the rate of evolution of the universe is also very large, right? Okay. So you have to measure in that time scale. Okay. So
Yeah,
delta T may
I
be
mean,
small in
at
absolute
that time
terms.
it would have made a difference.
Yeah,
Like
that time it would have made a difference. So at say 0.1 and 0.2, right? Here there'll be some lambda 1, okay, and here there'll be some lambda 2. Okay, and in general, lambda 1 over lambda 2 will be large. Right? Because by the time you are saying it will come after a short time. But in that short time, the lambda would have expanded very fast, right? The lambda dot over lambda is large in general at that time. So even in that short time, lambda could have doubled its size, for example. Right? Because this is large. This scale is set by the time scale in this regime, right?
okay.
So because of this, right? I mean, in absolute terms, maybe small. It is a small time, right? It not have in seconds, for example. But in 1 second, you can see the lambda will increase tremendously, right? In 1 second, right? Since the Big Bang, okay, that's of the time when the temperature has come down to 1 MeV. Okay, we'll do this calculation in more detail later, but roughly say an MeV, right? So lambda has gone from 10 to the 16 GeV, right? It's a ratio, it expands by 10 to the 16 GeV to 1 MeV within 1 second, right? So in seconds, it may be small, this the time difference, but that doesn't help in making lambdas the same. Right? This is a kind of, I mean, we can see in 1 second it increases by this factor, right?
Yeah, I think I'll have to calculate and convince myself.
Yeah, you have to calculate and convince yourself, but I think it will not help just just by the fact that the time difference is small in our usual sense.
I was thinking it was small, like so small that it might homogenize even with different starting points.
No, that will not happen. See, the point is you cannot, homogenize without paying a cost. I mean, what will homogenize? I mean, if these 2 points are out of the horizon, right? If at one point it's phi 2, another point it's phi 1, there's nothing that can homogenize, right? These difference will remain if they remain causally connected, disconnected.
Yeah, I was thinking that difference will be small. That difference will show up eventually in the reactions, like in the sense that at point one the reheating will begin at some time, and at point two the reheating will begin some delta t after that.
Yes.
But today, whatever experiment we do regarding like observing through the last scattering surface or whatever, that difference might not be relevant.
Yeah. So further you have to calculate this, right? This you can try
Yeah.
to certainly try to calculate using whatever equations you have, right? And you will find that these differences will not in general be small. Because by the time the second one has reached, right, this is now radiation dominated universe, and the universe has already expanded quite a bit.
Yeah. I mean, and also eventually, like if we were to keep on asking this question, what happens before, sort of a thing,
Yes.
like whether phi rolled from a higher value of like the potential, or what was it set at t equals 0 to this value or something,
Yeah.
that like abstract thing has to be non-local, right?
No, we don't know. Meaning the point is at 10 to the 19 GeV, right? We don't know what the physics is, right? Because that's quantum gravity. I mean, there the quantum effects of gravity become important. Right?
That is fine, but like just looking at some initial value, if we have to set that initial value in motion, like through some physical notion,
Yeah.
I mean, we can comment on whether that process has to be causal or non-local or local or something.
But the point is that may not even be a classical, they may not even have a classical description.
But I mean, the
You may not even
notion
have
of
to think of classically at this in this region.
notion of locality is not like entirely classical, right? I mean, it is just based on, I mean,
Oh, yeah. Okay. Yeah. But so why do you say that it has to be non-local?
because unless like otherwise it's I mean, like any initial value problem that we take
Yes.
let's say the t equals 0 is the initial point,
Yeah.
and we have to specify the field at all points in space time unless it's just a single point
Yeah.
in terms of space time.
Yeah.
So we have to specify at t equals 0 all space the value of phi in this case.
Okay.
Now if there is a theory that gives this phi,
Yes.
I would think it would be non-local, since it's setting all the at all space time point at all space points at the same time, some same value, well,
But
not the same
the
value,
point
but
of fluctuation, right? I mean, you do see if it's created quantum mechanically, then the quantum mechanics can set that fluctuation. See, as you will see that the inflation also, right? I mean, you could have asked the same thing for inflation. That what ultimately gives the difference between these values of phi at different points, right? It's a quantum fluctuation. So here the universe may have been created quantum mechanically, right? And then quantum fluctuations will give a distribution of phi in different regions. It could be totally random that we are the value of phi that is relevant for our patch, right, has some value, some is something, but that could just be a quantum effect.
but even that we'll call non-local, right?
No, quantum effects, okay. I mean, it's not. I mean, you're not changing non-local. You'll call something non-local if the dynamics is non-local. That if you are sending signals that is faster than the speed of light.
uh, okay.
And at present, we don't know what the story is here, right? So that's why, I mean, it's hard to say if it's local or non-local. But the point is, there is no reason why it has to be non-local.
All right.
Any other question?
Sir,
Yes, go ahead, please.
Sir, I have a doubt in lecture 9, page number 30.
In the earlier lecture. Okay, let me try to see if I can open this. So in the last lecture,
Yes, sir. Yes, sir.
okay.
Yes, sir. Sir, as we saw that the density, number density falling as temperature fall, that's imply the universe is expanding.
Yes.
Sir, I'm not understanding that the process like alpha bar, the density of alpha bar balancing the two-way process. That I got confused in this.
Yeah. So the point is that in general, the process is that suppose you have E plus E minus, right? E plus E minus can annihilate into two photons, and the two photons can collide and produce E plus E minus pair. Right? That's the balancing act, right? That's what we mean by thermal equilibrium. Okay. And so what would happen is that at some point, this thermal equilibrium, the way that you get out of thermal equilibrium is that E plus E minus annihilation rate. If that, for example, once the density of electrons becomes sufficiently low, see what is happening is that even in thermal equilibrium, the density of electron is falling, right? Because it goes as e to the minus m over t that we saw. Okay, that was probably in the previous slide. Yeah, that there is this exponential decay, right, for low temperature. So the number of electrons, the density of electrons is going down. And at some point, what will happen is that the E plus E minus annihilation rate will fall below the expansion rate. Okay, so a single E minus in a one Hubble time will not even encounter an E plus. Then this thermal equilibrium breaks down. You cannot apply the thermal equilibrium formula anymore. That means you cannot apply this formula anymore. Right? According to this formula, it will keep getting exponentially suppressed, right? As time goes on, because temperature is falling. Okay. But what will happen after this, after the system has fallen out of equilibrium, okay, is that this is what we call freeze out. Okay. Then the number density of electrons will be conserved, right? In this way, that n alpha times lambda cube, okay, this is the electron density times lambda cube, this will become constant because nothing is happening to those electrons, right? I mean, the density is depleting simply because of the expansion of the universe. Is that point clear? Okay, if it's not clear, you can ask again. Is it fine?
Yeah.
So basically, okay, we will discuss this in more detail later, right? How to calculate this rate, right? When this happens. But this is a physics that at some point, the reaction rate is so small that the assumption of thermal equilibrium breaks down.
Basically, sir, we are saying the reaction rate is small as comparison to expansion rate of the universe.
Exactly.
Okay.
That's right. When the reaction rate becomes smaller than the expansion rate of the universe, then you cannot apply the assumption of thermal equilibrium anymore.
And that freezing out condition will be coming. This freezing out condition will come.
Yeah. So we'll write down more in explicit equations what the freeze out condition is.
Okay.
But the physical idea is this one.
Okay. Thank
you. Okay. Any other question? Okay. If not, let me then begin. Okay. So I think there may have been some confusion about how exactly what we know and what we don't know. So let me first write down the details, okay, of how we go about solving the equations, right? What we mean by we have in thermal equilibrium, we in a sense know everything. Okay. So let's suppose that we have a system in thermal equilibrium. So at this stage, we are not even doing cosmology. Okay. Afterwards, we are going to apply it to cosmology. Suppose you have a system in thermal equilibrium with L conserved charges. thermal and chemical. Okay, I should say thermal and chemical equilibrium. Okay, that means whatever particle number has to be exchanged, it's allowed to exchange. Okay, subject to the conservation laws, of course. Then the claim is that then the state of the system is completely specified by the temperature and the densities NL of the conserved charges. Okay, so which means when we say the state of the system is completely specified, this means that we can calculate Ni, Pi, Rho I, all thermodynamic quantities, Si, etc., for each species, for each type of particle. Okay, not just the conserved charges, but this for each type of particle. Okay, and the route that one follows to do this is that knowing NL, sorry, I should have called this N tilde L, that's what we are calling the conserved densities, knowing N tilde L and T, okay, this can be used to calculate the corresponding chemical potentials mu tilde L. Okay, we describe in detail how to do that. Okay, this in turn determines the chemical potentials mu I, okay, by this formula, sum over L equal to 1 to capital L C Li mu tilde L. Okay. And once you know mu I and T, okay, then this can be used to calculate Ni, Pi, Rho I, Si in terms of mu I and T, okay, using the standard statistical formula. Okay, which again I'll try to write down later today. Is this clear? Okay, so now we turn to application to cosmology. So in cosmology, okay, N tilde L's are conserved. This is 0, which basically means that the N tilde L I can write as some constant KL over lambda cube. These are constants fixed by some initial condition. Okay, and here let me remind you that after inflation all the conserved charges are 0, but what you are talking about here is at the standard model scale. Okay, and there may be some conserved charges, okay, and the non-zero value, okay, presumably arises from some physics between the inflation and standard model scale that violates those charges. Okay, otherwise that all charges will be always 0. Okay, so any conserved charge that is created, okay, that we have with the in standard model scale, okay, must have been created somewhere between the inflation and the standard model scale. Okay, but in any case, for our purpose, okay, at a given epoch, we have a set of conserved charges, and those are given by this formula, okay, some constant over lambda cube. Okay, so at this stage, T and lambda are independent variables. Because N tilde L's are given in terms of lambda, right? And this basically means that we can now determine the all of these quantities, Ni, Pi, Rho I, Si, etc. in terms of lambda and T. So this means that Rho I, Pi, Ni, Si, etc. are known in terms of lambda and T. Okay. Now we apply energy conservation, okay, or equivalently entropy conservation. Okay, so now apply energy conservation. Okay. Or equivalently entropy conservation. Okay, in fact, entropy conservation is easier to use. d dt of S lambda cube equal to 0. Okay. So S lambda cube is constant. Okay. S is sum over I equal to 1 to k. K is the total number of spaces, Si. Okay. So the SIs are all given in terms of T and lambda, right? SIs are all given in terms of T and lambda because n tilde L is a function of lambda, T of course is an input. Okay. So using this, so this determines T in terms of lambda. And we will see some particular special cases later. Is this point clear? Okay. So in the second step, because we had two variables, T and lambda, now what we are saying is that either the energy conservation or equivalent to the entropy conservation, which followed from energy conservation, just derived using the energy conservation equation, we can determine T in terms of lambda. And now the final step is to use Friedman equation. Which is lambda dot over lambda squared plus k over a naught square lambda square at 8 pi g over 3 times rho. Okay. So rho is given by sum over I equal to 1 to k rho I. Okay. And rho i's are known now as function of lambda. Okay. So this gives a differential equation for lambda. And this can be solved to find lambda of T. Okay. And once you have found lambda of T, we know everything because everything else has been determined in terms of lambda. Okay. And some constants of integration. Are there questions? Okay. So now let me write down the ideal gas results again, okay, because we're going to use it. So ideal gas results. So we had P over T, which is 1 over V log Q. That was given by minus or plus G over 2 pi squared. Then N, this is for every particle, right? I should, if you so this is not a total P. Okay, and then later on I'll use these for total P, total N, etc. But I'm writing it for everyday spaces. So one should have ideally written a I here. Okay, I'm just writing this I just to avoid cluttering. So N is G over 2 pi square integral 0 to infinity K square dk. And here you have e to the minus beta minus mu. So again, the top sign is for the bosons and the bottom sign is for the fermions. Okay, in all of these formulae. And rho is the more or less the same expression, except that it's multiplied by the energy. Okay, we are going to make use of this later. So then we also said that for many applications in cosmology, this is not always true, and we'll see examples where this cannot be assumed. For many applications of cosmology, we can assume that the conserved charges are all zero. Okay. Basically because they are very small. Okay, whatever conserved charges we have are small. Okay. So this is simplifying assumption, but if you do that, then that basically means that N tilde L is equal to 0. And then we saw that as a consequence of this, mu tilde L vanishes. Okay. And this in turn means that mu i's vanish because mu I is given by linear combinations of the mu tilde L's. Okay. And in that case, the formula is simplified. Simplify. And this is what we'll assume from now. Okay. So then we studied the non-relativistic limit. So let me write down this formula again because there is a confusion about factors of 2. Okay. So P over T in the non-relativistic limit is T much smaller than M. P over T was given by Gm over 4 pi square e to the minus M over T square root 2 pi M over beta cube. Yes, go ahead, please.
Sir, I just want to clear, sir. In a statistical analysis, like sir, we are assuming that there is a matter-antimatter equality in the universe. Like,
yes, because the point is the matter there is a matter-antimatter asymmetry. Okay, today, but we saw that the number of photons to the number of excess baryons is very large, right? Like 10 to the 8.
okay.
So because of this, in the early universe, right, where photons and the radiation was dominating, this excess matter plays very little role for most analysis, but not always, right? And later on, we will see the cases where we cannot ignore this asymmetry, and there we will take into account this asymmetry.
Okay, okay, sir.
Okay, but for many purposes, we can simply ignore this asymmetry. Okay, and we are assuming that the matter and antimatter are equal.
Okay, okay.
Okay, P over T is this. N was Gm over 4 pi square e to the minus M over T square root of 2 pi M over beta cube and rho was basically m times n. So gm square over 4 pi square e to the minus m over t square root of 2 pi m over beta q. Okay, and essentially the point to notice is that all of these are exponentially suppressed. So all of these are exponentially suppressed. Okay, so if they remain in thermal equilibrium, their densities and other thermodynamic quantities fall very fast. Okay, as temperature is going down, these things all fall very fast. Okay, now we are going to study the opposite limit, which you can call the ultra relativistic limit. So ultra relativistic limit. Here T is much larger than m. Okay. So typical momentum that the particles carry. Okay. So typical momentum, okay, is much larger than m. Okay. So essentially we can replace this k square plus m square by k. Okay, that means you are essentially considering massless particle. Okay. In this case, we can write p over t with this formula minus plus g over 2 pi square integral 0 to infinity log 1 minus plus e to the power minus beta times k square dk. Okay. And now I'm going to scale beta. Okay, I'll write beta times k equal to u. Okay, change variable. To write this as minus g over 2 pi square. So I'm basically replacing k by u over beta. Okay. So beta to the minus 3 because it's k square and dk. Integral 0 to infinity du log 1 minus plus to the minus u. U square, I forgot. U square du. Okay. So this quantity is just a number. Okay. This is a number. We can calculate it. In fact, if you can just put it in mathematics and ask it to evaluate. Okay. It gives exact results. Okay. So the number happens to be minus pi to the 4 over 45 for bosons for the upper side, and 7 pi to the 4 over 360 for fermions. Okay. So using this, we can write this as, okay, let me write it. Say g over 2 pi square t cube. Okay. And this with a minus plus sign, okay, I'll write as AB times pi square by 3 times 1 or 7/8, okay, with top sign referring to bosons, bottom sign referring to fermions. Boson is to fermion. Okay. So what is AB? Okay. AB is in fact just a number, pi square by 15. Okay. So this is, I mean, you may wonder why we invent a symbol for just a number. Okay. We have invented it because it simplifies things a lot. Okay. And in fact, I mean, hidden inside AB will be some parts of H bar and C. Okay. And we will see why AB was introduced in the first place. Okay. In fact, it comes from the formula for the energy density of black body radiation. Okay, so AB is, for our purpose, AB is just pi square by 15. So you can see that pi square by 15 times pi square by 3 is pi to the 4 over 45. That's this number. Okay, the minus sign cancels this minus sign. And This one is just 7, 8 times the same number. Okay, that's how I have written it this way. Okay. And now we see that this pi square and this pi square cancels. Okay. So we can write P as G over 6 is G over 6 AB T to the 4, because this, I brought this T on this side. Write it properly. This is G over 6 AB T to the 4 times 1 or 7, 8, depending on if it's a boson or a fermion. Is this clear? Are there questions? Okay, so we can similarly calculate n. So n is G over 2 pi squared integral 0 to infinity k square dk e to the power minus beta k over 1 minus or plus e to the minus beta k. Okay. Again, we substitute beta k equal to u. Okay. So you get G over 2 pi square, okay, then t cube. Okay, basically 1 over beta q I'm writing as t cube integral 0 to infinity u square du 1 over 1 minus plus e to the minus beta u. Okay. And this number, this is again a number, sorry, e to the minus u, not beta u. Okay. So this is again a number, and you can again put it in mathematics and evaluate it. Okay. So this turns out to be 2 zeta 3 for bosons, okay, and 3/2 zeta 3 for fermions. Okay. So what is zeta? Okay, so zeta n is defined.
That will be 1 by e to the plus u minus minus plus 1, right? I mean, sorry, 1 minus plus e to the plus u.
Sorry. I the top one I should have written correctly. Yeah, let me write it as e to the power minus. Oops. E to the power minus u. This is okay?
Yes, yes.
Okay, so I just replace beta k by u, right? So we haven't got rid of this. So e to the minus u over this. So this is the result, and zeta n by definition, let me complete the definition, is sum over n equal to 1 to infinity, 1 over n to the s. Okay, so this is a convergent sum. Right? So for s equal to 3, for example, it's 1 plus 1 over 2 cube plus 1 over 3 cube and so on. Okay, so this is a finite series, and that's whatever that is called zeta 3. Okay. So n is proportional to t cube. Okay. So you can also calculate rho. So rho, you can of course substitute in the formula, but you can also use the thermodynamic relation. So rho is mu n minus del beta of p times beta. So this mu is 0. So mu is 0 in our case. So this is minus del beta of g over 6 ab beta to the minus 3. Okay. And then that number 1 or 7, 8, depending on if it's bosons or fermions. Okay. So this del beta gives you minus 3 beta to the minus 4. Okay. So this becomes g over 2 ab t to the 4 times 1 or 7, 8. Is this clear? Okay. And now you see that the significance of this number AB, even though it is just pi square over 15, okay, that for photons, G is 2, right? And rho will be ABTQ. And this is of course 1 because it's a boson. So rho is ABT to the 4, right? That's the way the AB was first introduced, okay? In the formula for the density, energy density of radiation, okay? AB times T to the 4. Okay. And you also see that for both bosons and fermions, P was for G over 6 times AB beta to the minus 3, right? So rho P is equal to rho by 3 volts for F and B. Okay, so there's a standard formula between the relation between pressure and energy density of radiation. Okay. Because P had a G over 6, otherwise it's the same, right? Let me show you here. It had a G over 6 times ABT to the 4. Right? Here you have a G over 2 times ABT to the 4. Are there questions? Okay, so let me also write the formula for entropy now. So S is 1 over T times P plus rho minus mu n. Again, we are setting mu equal to 0. So this is 1 over T times P plus rho, that gives you half plus 1/6 AB T to the 4 times 1 or 7/8. So this is 2/3. So 2/3 ABT cube times 1 or 7/8. Is this clear? Okay. So these are for individual. So these results are for individual spaces. These results are for individual spaces, types of particles. Okay. So the total pressure, for example, so P is sum over I equal to 1 to kPi. Okay. So this will be given by 1/6 AB T to the 4, okay, times sum over I GI. Okay, this is GI for individual particles. Okay, the number of states for ith kind of particle, okay, times either 1 or 7/8 depending on if it's a boson or a fermion. Okay. So this number plays an important role. Okay. So this number, what we'll call G effective. And because the same combination appears also in the energy density and entropy, we have rho as half ABT cube T to the 4 times G effective, and S is 2/3 ABT cube times G effective. Is this clear? So to calculate G effective, you have to basically count the number of bosons we have, multiply this, but each of them by the degeneracy, add them up, and then count the number of fermionic states you have, multiply them by 7/8, then add them up. Okay, that's the way you calculate G effective, and we'll see some specific examples later. Are there questions? Okay, so now let's calculate something. So now suppose that you want to calculate. So suppose you want to calculate the variation of T temperature with lambda. As we have discussed earlier, we can either use energy conservation or entropy conservation, but it's somewhat easier to use entropy conservation if you are in thermal equilibrium. Okay. So use d dt of s lambda cube equal to 0. So if you know the formula for s as a function of t, okay, you can find t as a function of lambda, right, by solving this equation. Now let's suppose that t is such that for every particle spaces, for every particle spaces I, either t is much larger than mi or t is much smaller than mi. For some particles, t may be much larger than mi. For some other particles, t may be much smaller than mi. Okay. But there is no I, no particle such that t is of order mi. Okay. And in fact, most of the history of the universe is like this, right? Because the particles, the masses are of course scattered, right? And when t is in between particle masses, okay, and this approximation holds. Okay. So let's suppose this is true. Okay. Then what would happen is that for particles for which t is much smaller than mi, okay, their contribution to entropy, energy density, pressure, etc., will be exponentially suppressed. So we simply ignore that contribution. For particles for which t is much larger than mi, okay, we treat them as ultra-relativistic particles. Okay. We use the formula that is given for mi equal to 0. Is this clear? So then S will be given by 2/3 AB T cube times some G effective, where G effective will include contribution from particles for which T is much larger than mi. And now we can easily see that this equation over here will tell us that T times lambda is constant. So T falls off as 1 over lambda. Okay, we had seen this in the context of CMB earlier, but it's also true in general. Okay, whenever the universe is radiation dominated. Okay, so this clearly is a situation where universe is radiation dominated because it may have some matter. Okay, for which the T is much smaller than the masses, but their densities become so small. Okay, as long as they are in thermal equilibrium, that we can ignore that contribution. Okay, that's what this is saying. Are there questions? Okay. So this formula certainly fails. So this fails when T of order mi for some I and in this case more detailed analysis is needed. Okay, and we'll do it later. Okay, we'll see examples later. Okay. But for now, we ask a simpler question. Okay. For now, ask a simpler question. So take two epochs. One where the epoch 1 is when t is much larger than mi for some I, and epoch 2 is when t, let's call it t1, t2 is, okay, let me not put the 1 and 2 label here right now. The epoch 2 is t is much smaller than mi for the same I. For the other particles, things remain the same. Okay, if t was much larger than mj, it remains still much larger than mj. If t was much smaller than mj, it remains smaller than mj. Okay, but some particle has gone from being relativistic, ultra relativistic to non-relativistic. In that case, we can ask what is the relationship between the temperatures above and below. Okay. So let me do this in a little more detail. So suppose T1 lambda 1 G effective 1 refer to quantities at some time in epoch 1. Okay, when T was much larger than mi. Okay. Lambda, and these are the values of the corresponding quantities G effective and lambda. So T2 lambda 2 G effective 2 refer to quantities at some time in epoch 2. Now, G1 effective and G2 effective are different because some particle which was contributing here, okay, in particular the particle of mass mi that was counted as relativistic here, it stops contributing here. Okay, so you count their contribution out. Okay, so G1 effective is larger than G2 effective if this was earlier and this is later. Is my voice audible? Because I got a message the internet connection is not stable.
It got cut for a second.
Okay, fine. So
Could you repeat the G effective part? Why is G effective 1 larger?
because this is, we are assuming that this is epoch 1 earlier. Okay. This is earlier. Earlier means higher temperature. This is later. Okay. So at higher temperature, right, the T1 was larger than mi for some particle. Okay. So it was relativistic, its contribution was to be included in G1, right? In G effective. Here the particle has gone non-relativistic. Okay. So its contribution to pressure, entropy, energy density, everything is small. Exponentially small. So we simply drop this from our counting.
Okay.
Okay, so that's the reason why G1 effective is larger than G2 effective. Is this point clear? We are basically dropping the non-relativistic particles from this counting simply because their contribution gets exponentially suppressed.
Yeah.
Okay, so now we can still apply entropy conservation because they are assuming thermal equilibrium.
Sir?
Yes, go ahead, please.
Sir, I have a doubt. Sir, in the two epochs, so the nature of the particle will be same or different?
No, nature of the particle is the same, right?
Okay.
Imagine that the particle is the electron, right?
Yes, sir.
At epoch 1 corresponds to the temperature when T is much larger than 0.5 MeV, okay, much larger than the mass of the electron. So electrons are considered as relativistic in that case, right? Massless particle, and this will get contribution from the electron. This corresponds to a temperature that is much smaller than 0.5 MeV, right? So the electrons are non-relativistic. So G2 will not get contribution from the electron, right? Because electrons have become exponentially suppressed. Their densities have gone down by exponential factor. But the nature of the particle is the same, right? Electron still remains the same electron, right? Its interactions are the same and so on.
Okay.
So here we can still use entropy conservation. So we get T1 lambda 1 cube, sorry, T1 cube, sorry, what did I say? T1 cube G1 effective lambda 1 cube is T2 cube G2 effective lambda 2 cube. Okay. So this tells us that T2 will be given by T1 times G1 effective times lambda 2, sorry, lambda 1 by lambda 2. Is this clear? So this is saying, you see that if T had gone as 1 over lambda, then T2 would have been T1 times lambda 1 over lambda. Okay, because T would have been proportional to 1 over lambda. This factor is telling us that T2 is larger than expected from 1 over lambda behavior. Okay. Because G1 over G2 is large. G1 is larger than G2. The physics behind this is that the entropy has gotten transferred from the massive particle to the massless particle. So earlier, in epoch 1, the entropy was being carried by the particle, all the nearly massless particles, including the one, who's the ith particle, right, that we have been talking about. Okay. Here, the entropy is carried only by the particles which still remain light. That means the ith particle is excluded. But the ith particle entropy has to go somewhere, right? And that entropy has now become part of the entropy of the other particles. Okay. And that's the reason why the effective temperature of the particles now is a little higher than what would have naively expected from the T goes to 1, T of order proportional to 1 over lambda behavior. Is this clear? Okay. So let me now turn to the notion of freeze out or decoupling. I have already introduced it earlier, but let me do it again. So decoupling or freeze out. So let me describe the thermal freeze out here. Later on, we'll discuss chemical freeze out. Okay. And I have already emphasized what this means. Okay, but let me do it again. Okay, that suppose in some epoch, the interaction of a particle, the interaction rate of a particle, or interaction rate of some particle falls below the expansion rate. which basically means that the average rate of collision is less than, okay, per unit time. Let me write per unit time is less than lambda dot. Okay, this is the expansion rate, or lambda dot over lambda. Lambda dot over lambda. Okay, these are roughly the time in which it e-folds. It goes with the size increases by a factor of e. So in that case, what is going to happen is that the particle falls out of equilibrium. Falls out of equilibrium. Okay. And as a result, rho I, pi, etc. are no longer given by the statistical formula. Okay. But of course, you have to keep doing cosmology, right? So they can still contribute to energy density and pressure, and hence they entered the Friedmann equation. Okay. So even though they are not given by statistical formula, you have to find a way to determine what the formula, what they are. Okay, after freezeout. Otherwise, you cannot do cosmology, right? Because there could be particles which have frozen out. Okay. So what we'll be describing is how to do this. Okay. So first, we consider a number density. N will fall off as 1 over lambda cube. Because if the particles are not interacting, their number per co-moving volume remains fixed, because the number of particles is now constant. So by the standard formula, N will fall off as 1 over lambda cube. Okay. So I can write this in more detail, more specific. This is NF lambda f cube by lambda cube, where lambda f is the value of lambda at freezeout. And NF is the number density at freezeout. Number density at freezeout can be calculated from statistical formula, right? Because it was in statistical equilibrium at that time. Okay, after that it has stopped being in statistical equilibrium. But we want to know how to calculate rho f. How to calculate rho? Question is how to calculate rho. Energy density. Okay. And for this, you have to do a little more work. Okay. What we need to know, okay, is that if we have a given particle of energy E, okay, then how does its energy change, okay, in the co-moving frame, okay, with time? Okay, so we need to study how the energy of a free particle change with time. Okay. So because of the homogeneity and isotropy, means that we can assume that the particle starts at t equal to 0. Sorry, not at t equal to 0. At the origin at r equal to 0 and moves outwards, moves radially outwards. So in this case, the proper time d tau squared, which is minus ds squared, will be given by dt squared minus at squared dr squared. Okay, we are ignoring the k. Ignore the curvature term. Okay, so this is from a metric. Okay, d theta d phi I have ignored because it's moving radially outwards. Okay. So you can write down now the action of the particle. See, our goal is that we have to study the equation of motion of the particle, okay, and see how its energy changes. Okay, because that's what you have to figure out, right? Because each particle, the particles have now fallen out of equilibrium, they are free streaming, right? They are moving freely. Okay. But moving freely doesn't mean in a expanding universe, moving freely doesn't mean that the energy remains constant. Okay. In Minkowski space, the energy will have to remain constant. Okay. But because it's the expanding universe, you have to figure out how the energy is changing. Okay, and that's what you are trying to do now. Okay. So the action of the particle is given by integral du. Okay, u is just an arbitrary parameter, times minus g mu nu dx mu du dx nu du to the power minus half, to the power, sorry, not minus half, to the power half, which I can also write as integral du times dt du square minus a of t square dr du square.
Sir?
Yeah, go ahead, please.
Sir, I have a confusion. Sir, like when we are talking about Hubble time, so sir,
Yes.
in a one Hubble time, like particles remain in equilibrium, and after that they freeze out. Is it right?
No, it's that when this number, see what you are saying is that the number of collisions per Hubble time, okay, should be very large in order for thermal equilibrium to be established.
Okay, yes, sir, yes.
So when the number of collisions per Hubble time is less than 1, then the rate is not sufficient to establish thermal equilibrium. Okay. So the freeze out time is when the rate equals 1. When the rate equals Hubble expansion. So when this equality is satisfied, that's what we'll define as the freeze out time. We'll calculate the average rate of collision per unit time. When this is equal to lambda dot over lambda, we'll call that the freeze out time.
Okay, okay, sir. Okay, I got it.
So this lambda f, nf, etc. refer to that time.
Okay.
Is this okay?
Sir, yes.
Okay. Okay. So now what we are going to do is to write down the equation for R by varying this action, by using the variation principle. So the equation for R is obtained by requiring that delta of the action is 0 for arbitrary delta R. Okay, so let's vary. Delta action will be given by integral du times dt du square minus at square dr du square. Because you are varying, you get minus half, okay, then factor of half, and then the variation of this, right, with a minus sign because of this minus sign over here. So at square dr du times d du of delta r, and you have a factor of 2 because of this square over here. Okay. So this cancels, these cancel, and now we are going to do an integration by parts. Okay. To write this as integral du ddu, integral du, we write as a delta r and then ddu of this whole thing. Okay, because basically we are just integrating by parts, so whatever appears here appears there. So dt du square minus 80 dr du square to the power minus half times 80 square times dr du is equal to 0. Is this clear? Okay. So now we are simply saying that because delta is completely arbitrary, the equation of motion is d du of this equal to 0. Okay, so let me write that. So that means this is a constant. Okay, whatever is inside the square bracket should be constant, right? That's what the equation of motion is telling us.
The u is simply tau, right?
Well, no, u is an arbitrary parameter here. We can take u to be tau, but right now we are not taking u to be tau. U is an arbitrary parameter. This is reparameterization invariant, right? You can see that parameterization u, if you change u to some function of v, right? It just it takes the same, retains its form with u replaced by v.
Yeah.
Okay, so how you choose parameterize u doesn't matter at this stage, right? But eventually we'll choose u equal to tau, but right now u is arbitrary.
Yeah.
Okay. So let me write this equation again in here, then it will become clearer, I think. So dr, so this means dr du, sorry, dt du first, dt du square minus 80 square dr du square to the power minus half times dr du equal to constant. Okay. And you can easily convince yourself that the left hand side is invariant under reparameterization.
So an 80 square will also come.
Yes, thank you. There's an 80 square here, right? Is this correct? Let me check this. Yeah, 80 square. Okay. So the point is that this combination, right, is really u independent. Okay. So now we can choose u to be anything you like. So we can choose u to be tau. Okay. And if you choose u to be tau, then this tells us that this quantity now becomes 1, right? Because after all, using d tau squared is dt square minus 80 square dr square. Okay. We see that this, whatever was to the minus half, this is just 1. Okay, because dt d tau square minus 80 square dr d tau square is just 1. Okay. So this tells us that 80 square times dr d tau is constant. Let me call it C. Okay. So dr d tau is C over 80 square. Is this clear? So we want to calculate actually dt d tau, okay, for a reason that I'm going to explain in a second. So dt d tau, okay, from here, because this is just 1 which you replace by tau. Okay. So this is 1 plus at square dr d tau square to the power half. Okay, that this basically follows from here. So this is one plus c square over at square to the power half. Is this clear? Okay, so you're almost done. Let me just complete this and then I'll stop. Okay. So the energy of the particle, so energy of the particle in the co-moving frame so you are saying co-moving frame because you are thinking of t as a time, right? Cosmic time as a time. That's given by m times dt d tau, right? This is a general formula. Okay. So if you now substitute this, we see that this is m times 1 plus c square over at square to the power half. So I can also write as m square plus c square m square over at square. Okay, the power half. Is this clear? Okay. Now suppose that at t equal to tf, the particle has energy m square plus k square to the power half. Right? That's the standard formula for the energy that we have been using. Okay. Then this tells us, okay, that this c squared m square, okay, by af square, okay, or artf, so that's af square is k square. Okay. So c square m square is k square af square. Okay. So then energy at time t, energy at time t at time t, okay, we use this formula. Okay. Except that c has now been determined by this formula, right? So that's m square plus k square af square over at square. But this I can also write as to the power half m square plus k square lambda f square over lambda square to the power half. Is this point clear? Okay. So what this is saying is that if a particle starts, okay, by carrying momentum k, okay, that is given in this formula, okay, and here I mean, if we want to avoid the question of which frame the momentum is in, we can just think of in terms of energy. If the particle starts with energy m square plus k square to the power half, okay, then after time t, its energy takes the form of m square plus k square lambda f square over lambda square to the power half. So effectively, k has gotten scaled by a factor of lambda f over lambda. So this is just a purely classical resultant GR. So next time we are going to use this to find the distribution of the energy density in the frozen out component of matter. So I think today my time is already up, so I'll stop here. Are there questions?
So can you go to the expression for where you compared the entropy at 2 epochs?
Compare the entropies at 2 epochs, okay? Here, right? This one?
Yeah. To calculate G effective, we also have to know which particles are contributing. I mean, which particles are free particles. At some time, electron and proton would be called a free particle, but after some time they would have recombined. So the degree of freedom has reduced.
Yes, certainly. That's so that we are not worried about right now, because as you have said that right now the level at which you are working, we are simply ignoring excess matter. But you are indeed right that we have to know which particles exist as free particles, right? Relativistic free particles. Right? That's what G counts.
What are we ignoring?
What are you doing? See here, for
What are
example,
we ignoring? What did you say we are ignoring?
right now we have set all the mu is equal to 0, right?
Yeah.
So this electron proton excess, right? That recombination, that we are not worried about right now, right? This formula, for example, we are going to apply when the temperature comes from above 0.5 MeV to below 0.5 MeV. So above 0.5 MeV, the E plus E minus would have been relativistic, right? So G on effective will get contribution from electron, positron, as well as whatever other particles there are at that time, like neutrinos. Whereas for temperature below 0.5 MeV, the electron contribution will go away. The neutrino contribution will still remain. So this G2 effective will now have to be recalculated only with only neutrino contribution. So that is a kind of situation we are thinking of right now. Right?
Okay.
Recombination that you are referring to, right? That involves, that comes at a much later stage, and also at that stage, of course, mu is not, you cannot ignore mu anymore, right? Because the excess density is basically there the excess density dominates the rest, right? There is no proton antiproton combination left, for example, right? Those have all died out.
Okay.
So this is assuming mu equal to 0, right? So no excess matter or antimatter.
Yeah, I think what he was saying, like this will never happen for electron, because before the T goes below 0.5, it will have already recombined, because the temperature need only be 1 electron volt, right? When the recombination happens.
Yeah. But you are coming down from top, right?
Yeah, so electron as a radiation exists above that, but
above 0.5 MeV.
Yeah.
Right? And electron becomes non-relativistic at less than 0.5 MeV.
Yeah, but we need not include it into this, because it is not in equilibrium anymore. It will would have recombined already.
No, 0.5 MeV. That time electrons remain as free electrons, right? It recombines at of the order of electron volt.
Oh, sorry, I was thinking of milli electron. My bad.
No, yeah, it's electron volt. So that happens at a much later stage. So at this stage, protons and electrons all are can be thought of as free particles. In that proton, okay, again, excess proton will ignore, right? So number of protons actually is, according to this formula, will be very, very low, right? Because proton mass is of the order of 1 GeV. So proton has already decoupled. So G1 effect, neither G1 effective nor G2 effective will include the contribution from the protons. Right? Because that's down by factor V to the minus 1000, right?
Yeah.
if you ignore mu. So we'll see that when we apply it to the case of this particular transition, okay, this is a general formula which can be applied to all transitions of this kind, right? For example, when the temperature comes from above the muon mass to below the muon mass, right? The same kind of formula will work. But where do we apply it? Okay, to the E plus E minus case, when the temperature falls from above electron temperature to below electron mass temperature, there basically it's only the neutrinos which remain, which contribute. Okay, all other particles have already become non-relativistic by then. Is that okay?
So,
Yes, go ahead, please.
sir, the things like we are doing, sir, that's only for radiation dominated era because we are ignoring the excess of baryon.
Yes, so we are certainly ignoring the excess of baryons, right? That we'll see later what the effect of that is.
Okay,
So this is at much early in the history of the universe.
okay.
Because at today, for example, there's no thermal equilibrium.
Yes, sir.
So you cannot apply thermal equilibrium formula anyway in the late universe, right? And we'll see later, I mean, at what point everything falls out of thermal equilibrium.
Okay, sir. Okay. Yes, I got it.
So this is at high temperature when thermal equilibrium was a good approximation, right? At least for most particles.
Okay.
Sir, if assume that if the inflaton fields decay width is very large, then I mean it will eject energy, right? So I mean, can we use this entropy conservation if this inflaton has a large decay width?
Well, if it's out of equilibrium, of course you cannot apply entropy conservation, right? So one has to check if the system remains in thermal equilibrium by comparing the expansion rate with the reaction rate. As long as the as long as the system remains thermal equilibrium, we can always use entropy conservation.
Yes. Okay.
So it's only when the system is driven out of equilibrium that the entropy conservation fails.
Okay.
Any other question?
I had a like for black holes, when people define something like entropy, they don't really mean entropy in the sense of what particles have, right?
No, black hole entropy is different, meaning it is apparently different, yes.
But is it some like here also we are saying something like some particles when they go from relativistic to non-relativistic, some entropy is transferred to the particles which are still relativistic.
Yes.
So that sort of an quote unquote entropy transfer happens for like black holes and other particles.
Yeah, that can happen, certainly.
Yeah, so in that sense, the entropies are same, like the notion of entropy.
Yeah, so thermodynamics, the notion of entropy was introduced for black holes because it obeyed the laws of thermodynamics.
That is like, we state it like that, or does it happen?
No. See, originally it was stated in analogy, right? But after the discovery of Hawking radiation, we know that it actually obeys laws of thermodynamics.
No, as in experimentally, no.
No, theoretically, right? In its interaction with other thermal system, it behaves as a thermodynamic object.
Okay.
Right? So that we know. I mean, it's not just an analogy, right?
No,
It was originally an analogy because it was only a classical analysis. But Hawking's calculation showed that it actually has a temperature, physical temperature, right? It emits black body radiation.
temperature in the sense that it is in equilibrium with its surrounding or something.
Yeah. If you put a surrounding at a given temperature, then it will be in equilibrium, right? The amount of radiation that will come out of black hole will be equal to the amount of radiation that will fall into the black hole. So the black hole temperature is the bath of the temperature of the bath, right? For which the net energy exchange is zero on the average.
Okay.
So it is a genuine thermal entropy that way. And as far as thermodynamics is concerned, it behaves exactly as entropy.
Yeah, all right. Thank you.
Okay, so I think I have to stop because the next class will start. So we'll meet tomorrow.